Somewhere over the vast gray expanse of the Pacific Ocean, a jet aircraft launches off the deck of an American supercarrier, climbs into the sky, and begins flying a precise, calculated route toward a thirsty fighter jet burning fuel miles away. The pilot of that fighter exhales in relief. But here is the part that will change everything you thought you knew about modern naval aviation. That tanker aircraft has no pilot. No human being sitting in that cockpit. No hands on the controls. Just artificial intelligence, sensors, and decades of American aerospace engineering operating with machine-level precision at 30,000 feet above a merciless ocean. This is not science fiction. This is not a concept from some future battlefield. This happened. This is real. And the machine that made it possible, the Boeing MQ-25 Stingray, may very well be the single most transformative development in carrier aviation since the jet engine itself. Welcome to the story of how the United States Navy quietly rewrote the rules of aerial warfare, and why almost nobody outside of specialized defense circles is talking about how enormous this really is. To understand why the MQ-25 Stingray matters so deeply, you have to go back. You have to understand what a carrier strike group actually is, what it can do, and more importantly, what its most painful limitation has always been. When the United States Navy deploys a carrier strike group, that floating city of steel carrying thousands of sailors, dozens of aircraft, and enough firepower to reshape the politics of entire regions, it does so with enormous confidence. But that confidence has always carried a secret vulnerability at its core. Range. The range problem. It is the problem that has haunted naval aviation planners for decades, and it became especially critical in the 21st century when potential adversaries like China began developing sophisticated anti-ship missile systems specifically designed to push American carriers further and further from the coastlines they needed to threaten or protect. The aircraft that fly from those carriers, the F/A-18 Super Hornets, the F-35C Lightning IIs, are extraordinary machines. They are fast, lethal, stealthy, and packed with the most advanced sensors and weapons systems on the planet. But they have a fundamental constraint that no amount of engineering brilliance can fully overcome without external help. They carry a limited amount of fuel, and when that fuel runs low, they need more. In the early decades of carrier aviation, this problem was managed through a combination of mission planning, strategic positioning, and the use of dedicated tanker aircraft that could transfer fuel from one plane to another while both were flying. This process, aerial refueling, became one of the most critical and logistically demanding aspects of any sustained air campaign. And for the Navy, doing this from a carrier deck introduced complications that land-based air forces simply never had to deal with. For years, the Navy relied on a system called the buddy store, where fighter jets themselves would carry an external fuel pod and act as tankers for other fighters. You heard that correctly. Fighters were being used to refuel other fighters. It worked, but it was deeply inefficient. Every time you took an F/A-18 and turned it into a tanker, you lost a combat aircraft from your strike package. You reduced the offensive power of your carrier air wing. You burned precious flight hours on aircraft that were supposed to be fighting, not serving as flying gas stations. It was a compromise born of necessity, and it frustrated naval aviation planners for an entire generation. The dream was always the same: a dedicated, purpose-built carrier-based tanker that would free fighters to fight, extend their reach dramatically, and do so without requiring a human pilot to take on what was, in the grand strategic scheme of things, a support role that could theoretically be automated. That dream began taking serious institutional shape in the early 2010s, when the United States Navy began developing the concept that would eventually become the MQ-25 Stingray program. But to understand why this program was so ambitious and so historically significant, you need to understand the broader context of what was happening in unmanned aviation at that time. The era of drone warfare had already arrived with the Predator and the Reaper in the Army and Air Force, but those were relatively slow, propeller-driven aircraft operating in permissive environments where nobody was shooting sophisticated air defense systems at them. What the Navy wanted was something fundamentally different. They wanted an unmanned aircraft that could operate from the deck of a nuclear-powered aircraft carrier. The most challenging launch and recovery environment in all of aviation. Fly at jet speeds, carry enough fuel to make a real operational difference, and survive in environments where adversaries would be actively trying to detect and destroy it. The technical requirements alone were staggering. Carrier operations are among the most demanding environments in all of aviation. Landing on a carrier deck requires hitting a moving target, a pitching, rolling, heaving surface in the middle of the ocean, at speeds over 150 miles per hour, catching one of 4 arresting wires with a tailhook, and coming to a complete stop in roughly 300 feet. Human pilots spend years mastering this skill. They still sometimes get it wrong. The idea that an unmanned aircraft could do this reliably, consistently, and safely was considered ambitious by even the most optimistic aviation engineers. And yet, that is precisely what Boeing and the United States Navy set out to prove. The formal program that became the MQ-25 grew out of an earlier, more ambitious project called the Unmanned Carrier-Launched Airborne Surveillance and Strike Program, known as UCLAS. In its original conception, UCLAS was supposed to produce an unmanned aircraft that could not just refuel other jets, but also conduct strike missions, penetrating enemy defenses and dropping weapons on targets deep inside contested airspace. It was an extraordinarily ambitious vision, and it generated years of debate inside the Pentagon, the Navy, and the broader defense community. Should the Navy's first carrier-based unmanned aircraft be primarily a tanker, a strike aircraft, a surveillance platform? The arguments were fierce, the requirements kept shifting, and the program repeatedly stalled under the weight of its own ambitions. Eventually, cooler and more pragmatic heads prevailed. The decision was made to focus the program on what was most immediately needed and most technically achievable: a dedicated aerial refueling aircraft. This was not a defeat of ambition. It was a strategic prioritization. The Navy recognized that the refueling problem was urgent, that solving it would deliver immediate and enormous operational benefits, and that developing an unmanned carrier aircraft in a tanker role would build the foundational technologies: autonomous carrier landing, deck operations, airspace integration, that would eventually enable more complex unmanned missions in the future. In 2016, the program was officially restructured and redesigned, and it was renamed. It became the Carrier-Based Aerial Refueling System, or CBARS. And shortly thereafter, the aircraft that would fulfill this requirement received its permanent designation, MQ-25, with the name Stingray attached to honor the sleek, flat, wing-shaped profile of its airframe. Now let's talk about the aircraft itself, because the MQ-25 Stingray is a remarkable piece of engineering that deserves careful examination. Boeing was awarded the development contract in September of 2018, beating out competing designs from Lockheed Martin and General Atomics, two companies with enormous experience in unmanned aviation. The fact that Boeing won this contract with a design that was notably more conventional and less stealthy than some of its competitors told you something important about the Navy's priorities. This was about operational reliability, carrier compatibility, and getting an effective tanker into service as quickly as responsibly possible. Stealth and strike capability could come later. The foundation had to be built first. The MQ-25 Stingray is a mid-size, subsonic, jet-powered unmanned aircraft with a blended wing body design that gives it that distinctive Stingray-like appearance. Its wingspan is approximately 75 feet, substantial enough to carry significant fuel loads while still fitting within the tight confines of a carrier flight deck and hangar bay. The aircraft uses a turbojet engine, giving it the speed and altitude performance necessary to operate effectively in the same airspace as the fighters it supports. It carries an aerial refueling store, essentially a specialized fuel pod with a trailing drogue and hose system mounted under its fuselage, and it can transfer thousands of pounds of fuel to multiple aircraft during a single mission. The exact fuel transfer capacity is classified, but publicly available estimates suggest the MQ-25 MQ-25 can significantly extend the combat radius of the F/A-18 Super Hornet and the F-35C beyond what was previously achievable with buddy store refueling alone. What makes the MQ-25 genuinely revolutionary is not just what it carries, but how it operates. This aircraft is designed to function within the existing carrier air wing without requiring massive changes to how the ship operates. It uses the ship's catapults, the electromagnetic launch system or legacy steam catapults, for launch, just like any other aircraft on the deck. It recovers using the arresting wire system, just like any other aircraft. The sailors who work the flight deck, the air boss who manages all flight operations from the ship's island, the pilots who fly alongside the MQ-25, all of them interact with this unmanned aircraft using procedures that are recognizable and compatible with what they already know. That integration philosophy was deliberate and critical. You cannot revolutionize carrier aviation by introducing a system so alien that it breaks the established routines and procedures that keep highly complex and dangerous flight deck operations safe. The control architecture of the MQ-25 is worth spending some time on because it represents a sophisticated balance between autonomy and human oversight. The aircraft is not fully autonomous in the way that a science fiction robot might be. It does not make its own strategic decisions. It operates under a command structure in which human controllers, working from the carrier's combat direction center or from dedicated control stations, establish the mission parameters, authorize specific actions, and maintain the ability to intervene at any point. But within those parameters, the aircraft exercises significant autonomous capability. It navigates independently. It manages its own fuel systems. Most impressively, it executes carrier landings, those incredibly demanding arrested landings on the moving deck, with autonomous precision guided by a sophisticated suite of sensors, cameras, and data links that feed into its flight control computers in real time. The autonomous carrier landing capability is perhaps the single most technically impressive achievement of the MQ-25 program. To understand why, consider what a carrier landing actually involves from a physics and engineering perspective. The aircraft approaches the carrier from the stern, flying a precise glide path angle of approximately 3.5 degrees toward a deck that may be pitching up and down by feet with ocean swells, rolling side to side, and moving forward through the water at speeds of up to 30 knots. The pilot, or in this case, the autonomous flight control system, must continuously adjust the aircraft's approach to compensate for all of these variables in real time. The approach speed must be exactly right. Too slow and the aircraft stalls. Too fast and it overshoots the wires. The tailhook must engage one of the arresting wires within a very small target zone. From the moment the aircraft crosses the ship's stern to the moment it stops, the entire arrested landing takes approximately 2 seconds. 2 seconds in which everything must go precisely right. The MQ-25's autonomous systems accomplished this repeatedly and successfully in testing, and that achievement alone represented a generational leap forward in unmanned aviation technology. Now let us walk through the history of the MQ-25 program in greater chronological detail, because the path from concept to operational aircraft was neither smooth nor simple, and understanding the obstacles that were overcome makes the final achievement far more impressive. The roots of the program, as we discussed, go back to the UCLIS initiative of the early 2010s. But the serious development work that led directly to the MQ-25 Stingray we know today began in earnest around 2016 and 2017, when the Navy finalized the restructured CBARS requirements and began soliciting industry proposals. For companies submitted competing designs: Boeing, Lockheed Martin, General Atomics, and Northrop Grumman. Each brought a different philosophy and technical approach to the problem. General Atomics, makers of the famous Predator and Reaper drones, proposed a design leveraging their deep experience in unmanned systems but adapted for the carrier environment. Lockheed Martin brought stealth expertise and a more advanced, combat-capable design vision. Northrop Grumman, which had already built the X-47B, an experimental carrier-capable stealth drone that had demonstrated autonomous carrier landings years earlier, offered perhaps the most technically sophisticated option, but also potentially the most expensive and complex. Boeing's winning design was notable for its relative conventionality and its emphasis on what the Navy actually needed right now rather than what might be theoretically possible in the future. It was practical. It was integrated. It was designed to work within the existing carrier air wing structure without reinventing every system around it. Boeing received the engineering and manufacturing development contract in September 2018, worth approximately $805 million, a figure that seems almost modest given the technological complexity involved. The company designated a test aircraft as T1 and began the long process of ground testing, systems integration, and envelope expansion that every new military aircraft must go through before it can be trusted to operate in the real world. The first taxi tests took place at Mid-America's St. Louis Airport in Illinois, where Boeing maintained a large development facility. Engineers spent months validating every system, checking every sensor, verifying every line of software code in the aircraft's flight control computers. This was painstaking, methodical work, the kind of work that rarely makes headlines but that determines whether an aircraft program succeeds or fails. The MQ-25's first flight took place on September 19, 2019, at Mid-America's St. Louis Airport. It was a milestone that naval aviation historians will record as genuinely significant. The first flight of what would become the first operational unmanned aircraft designed specifically to operate from a United States Navy aircraft carrier. The test flight was not dramatic in the way that combat missions or world speed records are dramatic. The aircraft took off, flew a defined test profile, and landed safely. But in that quiet, methodical success was contained an enormous amount of meaning. Decades of debate, billions of dollars of investment, and the work of thousands of engineers, naval officers, and defense contractors had produced an aircraft that could actually fly. The MQ-25 Stingray was real. The testing program that followed the first flight was extensive and carefully structured. Boeing and the Navy moved through a systematic expansion of the aircraft's performance envelope, testing its systems at progressively more demanding conditions. The fuel transfer system was tested on the ground and then in the air, first with surrogate aircraft and then with actual Navy fighters. One of the most important early milestones came in June of 2021, when the MQ-25T1 test aircraft conducted its first ever aerial refueling of a U.S. Navy aircraft in flight. The receiving aircraft was an F/A-18 Super Hornet. The refueling took place over the skies of southern Illinois, with the MQ-25 deploying its drogue hose and transferring fuel to the fighter jet in a controlled, successful demonstration. It was a historic moment, the first time in history that an unmanned aircraft had refueled a carrier-based fighter jet. The Navy released footage of the event, and for those who understood what they were watching, the implications were staggering. Further aerial refueling demonstrations followed in rapid succession, each one expanding the operational envelope and validating the system's reliability. In August of 2021, the MQ-25 successfully refueled an E-2D Advanced Hawkeye, the Navy's carrier-based airborne early warning and control aircraft, which was significant because the E-2D is an entirely different class of aircraft from the Super Hornet, with different performance characteristics and refueling requirements. Demonstrating that the MQ-25 could successfully transfer fuel to multiple different aircraft types was essential for proving its flexibility as an operational tanker. Then, in September 2021, came perhaps the most symbolically important refueling demonstration of the entire test program. The MQ-25 transferred fuel to an F-35C Lightning II, the Navy's most advanced and most expensive combat aircraft, a fifth-generation stealth fighter that represents the cutting edge of American air power. The sight of an unmanned aircraft refueling an F-35C in flight was, for those who had followed the long and difficult history of carrier-based unmanned aviation, almost surreal in its significance. Throughout 2022 and 2023, The MQ-25 program continued advancing through its development milestones, with growing attention turning toward the critical challenge of carrier integration, demonstrating that the aircraft could actually operate safely and effectively from the deck of a real aircraft carrier, not just from land-based test facilities. This required extensive coordination between Boeing, the Navy's Naval Air Systems Command, and the carrier fleet itself. The procedures for handling an unmanned aircraft on a carrier flight deck, one of the world's most dangerous and congested workplaces, had to be developed, tested, refined, and validated. Sailors who had spent years working with piloted aircraft had to learn new protocols for an aircraft that had no pilot to communicate with directly. The preparations for shipboard testing were meticulous. Mock-up flight decks were used to train deck crews. The aircraft systems were tested for compatibility with carrier-specific equipment: the catapults, the arresting gear, the visual landing aid systems, the carrier's data link architecture. Naval engineers worked through scenario after scenario, asking hard questions about what would happen if this system failed or that sensor malfunctioned, and building in the redundancies and safeguards necessary to ensure that a system failure would result in a safe outcome rather than a catastrophic one. The culture of carrier aviation is built on an almost obsessive attention to safety and procedure, and integrating an unmanned aircraft into that culture required respecting that culture, not overriding it. Carrier deck trials, the critical tests that would determine whether the MQ-25 could actually operate from a real carrier, were a major focus of the program's development timeline. The complexity of carrier operations cannot be overstated. Every aircraft on a carrier flight deck exists within a precisely choreographed ballet of movement, with hundreds of sailors working in extremely close proximity to aircraft that are being fueled, armed, taxied, launched, and recovered simultaneously. Every actor in this ballet has a specific role, a specific set of hand signals and communications protocols, and a deeply ingrained understanding of where they can and cannot safely stand at any given moment. Adding an unmanned aircraft to this environment without a human pilot in the cockpit to respond to unexpected situations required thinking through thousands of contingencies in advance. The software architecture governing the MQ-25's deck operations was extraordinarily complex. The aircraft needed to be able to respond to signals from deck handlers, follow taxi paths precisely in the confined space of a carrier deck, interface with the catapult system for launch, and approach and catch an arresting wire on landing, all while the deck itself was moving with the motion of the ship beneath it. The engineering team at Boeing worked for years on the algorithms and sensor systems that would make this possible. They drew on advances in computer vision, machine learning, sensor fusion, and control system design that would have been impossible just a decade earlier. Let us now step back and consider the broader strategic context that gives the MQ-25 program its deepest significance. We are living in an era of great power competition, a phrase that has become almost a cliché in defense circles, but that reflects a genuine and profound shift in the global security environment. China's People's Liberation Army Navy has been expanding at a historically unprecedented rate, building aircraft carriers, advanced submarines, and a vast arsenal of anti-ship ballistic and cruise missiles. Russia, despite its conventional military challenges elsewhere, continues to develop and field sophisticated anti-access and area denial systems. These developments have forced American defense planners to confront an uncomfortable reality: the era in which U.S. carrier strike groups could operate with near impunity close to any adversary's coastline may be ending. The response to this challenge is a concept called distributed maritime operations, essentially spreading naval power more widely across larger areas of ocean to make it harder for adversaries to target and destroy. But distributed operations require reach. They require aircraft that can fly further, strike targets at greater distances, and still return safely to their carriers. And reaching further requires fuel. More fuel than the current generation of carrier-based fighters can carry internally. The MQ-25 Stingray addresses this strategic problem directly by providing a dedicated, purpose-built refueling platform that does not consume a combat aircraft for the tanker role. The Navy can extend the effective combat radius of its carrier air wings significantly, potentially by hundreds of miles. In a world where an adversary's anti-ship missiles are designed to push carriers back to the edge of their aircraft's range, adding hundreds of miles of effective range back to those aircraft is not a minor tactical improvement. It is a strategic game-changer. Consider the numbers in concrete terms. The F/A-18 Super Hornet has an unrefueled combat radius of roughly 450 nautical miles. With aerial refueling from an MQ-25, that combat radius can be extended substantially. Estimates suggest to 600 nautical miles or more, depending on the specific mission profile and payload. For an aircraft carrier that is being pushed back by the threat of long-range anti-ship missiles, those additional miles can mean the difference between being able to strike a target and being unable to reach it. Multiply that capability across an entire carrier air wing, and the strategic implications become profound. The MQ-25 does not just solve a logistical problem. It directly counters one of the key strategic advantages that adversaries like China have been investing in for years. The F-35C connection deserves particularly careful attention. The F-35C Lightning II is the Navy's newest and most capable strike fighter, designed with the kind of low, observable stealth characteristics that allow it to penetrate sophisticated integrated air defense systems that would destroy older aircraft. But the F-35C's internal weapons bay capacity and its stealth requirements place constraints on how much external fuel it can carry without compromising its radar signature. This means that the F-35C, while extraordinarily capable at what it does, has range limitations that become significant in the kind of long-range power projection scenarios that the Navy needs to plan for in the Pacific. The MQ-25 can top off an F-35C's fuel tanks without requiring the fighter to carry external fuel pods that would compromise its stealth, allowing the F-35C to arrive at its target area with maximum fuel and maximum low observable capability. This is an extraordinarily powerful combination. There is another dimension to the MQ-25's significance that goes beyond the immediate tactical and operational benefits, the precedent it sets, and the path it opens. The MQ-25 is the Navy's first operational carrier-based unmanned aircraft, and while its initial role is specifically aerial refueling, the technologies it develops and validates will form the foundation for future unmanned systems with far more expansive capabilities. The autonomous carrier landing system, the deck handling protocols, the control architecture, the airspace integration procedures, the maintenance and support infrastructure. All of these things, once proven and refined through MQ-25 operations, become available for application to future systems. The Navy has explicitly discussed future variants or successor aircraft that could incorporate intelligence, surveillance, and reconnaissance capabilities. Strike capability. The original ambition of the UCLAS program remains a long-term goal that the MQ-25 program moves closer to by building the necessary foundation. This is how transformative military technologies typically work. They do not arrive fully formed and immediately capable of doing everything. They arrive at an achievable first step. They prove the core concepts. They build institutional knowledge and operational experience, and then they evolve. The Predator drone started as a slow, propeller-driven surveillance aircraft with no weapons at all. It evolved into the Reaper, which could carry bombs and missiles and conduct combat operations across the globe. The same evolutionary trajectory awaits unmanned carrier aviation, and the MQ-25 Stingray is the critical first step on that trajectory. The human dimension of the MQ-25 story is also worth exploring in depth, because one of the most interesting and underappreciated aspects of this program is how the Navy's human aviators, the carrier pilots who have spent their careers mastering the incredibly demanding art of carrier aviation, have responded to and engaged with this new unmanned system. Contrary to what one might expect, the response from the carrier aviation community has been largely positive, and the reasons for that positivity are instructive. The MQ-25 is not replacing fighter pilots. It is freeing them. Every Navy fighter pilot who has ever had to take a Super Hornet loaded with a buddy store tanker pod instead of weapons knows the frustration of flying a combat aircraft in a support role. The MQ-25 eliminates that frustration. It gives fighter pilots their aircraft back, fully configured for combat, not converted into a flying gas station. The relationship between human pilots and unmanned aircraft systems is one of the defining challenges of 21st century military aviation, and the MQ-25 program offers important lessons about how that relationship can work productively. The key insight is that the question should never be framed as human versus machine. It should be framed as how do humans and machines together create capabilities that neither could achieve alone. The MQ-25 Stingray cannot decide what targets to strike, cannot exercise the kind of judgment that experienced combat pilots develop over careers of flying, cannot adapt dynamically to the full complexity of a real-world combat environment. But it can fly a refueling track for hours without fatigue, can execute carrier landings with machine-level precision, can transfer fuel to multiple aircraft in sequence without the pilot workload penalties that would accumulate for a human tanker pilot. Human pilots and unmanned tankers, operating together as a team, are more capable than either could be independently. The program's development also touched on questions about the future of naval aviation careers and the evolving role of aviators in a world where unmanned systems are becoming increasingly capable. These are not hypothetical or distant questions. They are questions that young naval aviation candidates are thinking about right now as they decide whether to pursue careers in military aviation. The Navy's answer, at least as embodied in the MQ-25 program, is reassuring. The skills, judgment, and decision-making capability of experienced naval aviators remain irreplaceable, and unmanned systems are tools that enhance rather than replace human military professionals. Let us now spend some time on the industrial and programmatic story of the MQ-25, because the relationship between Boeing, the Navy, and the broader defense industrial base in developing this aircraft is itself a fascinating story about how large, complex defense programs navigate the tension between technological ambition and programmatic reality. Boeing's victory in the MQ-25 competition was not universally celebrated in the defense industry. Some analysts argued that the Navy was leaving too much capability on the table by choosing a relatively conventional, non-stealthy design when more advanced options were available. The counter-argument, the one the Navy found persuasive, was that getting an effective, reliable, carrier-compatible unmanned tanker into service sooner was worth more than pursuing a technically perfect but potentially delayed and cost-overrun alternative. The history of American defense procurement is littered with programs that pursued perfection and achieved neither that perfection nor a timely delivery. The F-35 program itself is a cautionary tale of what happens when requirements grow too ambitious and development timelines stretch across decades. The Navy, in choosing Boeing's more conservative MQ-25 design, was making a deliberate bet that operational relevance achieved on a reasonable timeline was more valuable than theoretical excellence achieved at some uncertain future date. Whether that judgment was correct remains a subject of debate among defense analysts, but the outcome, an aircraft that has demonstrably succeeded in its core test objectives and is moving toward operational deployment, suggests the pragmatic approach had merit. Boeing's industrial approach to the MQ-25 drew on capabilities and technologies from across the company's long history of military aircraft development. The aircraft's airframe draws on design principles developed across decades of military work. Its flight control software incorporates advances in autonomous systems developed through various research programs. Its manufacturing reflects Boeing's experience producing complex military aircraft at scale. The company's approach emphasized reliability and maintainability, designing the aircraft so that carrier-based maintenance crews, who operate under extremely challenging conditions at sea, can keep it flying with the tools and spare parts available on a deployed ship. The logistics of supporting an unmanned aircraft in the carrier environment is itself a non-trivial challenge. Unlike piloted aircraft, the MQ-25 does not have a pilot who can provide real-time feedback about how the aircraft is behaving, what unusual sounds or vibrations might indicate developing problems, or how the aircraft systems felt during a particular maneuver. Instead, the maintenance crews and the engineers who support the program rely on an extensive suite of onboard sensors and data recorders that continuously monitor the aircraft's health and transmit that information to maintenance personnel. This kind of data-driven maintenance approach, sometimes called condition-based maintenance, is actually an area where unmanned aircraft have inherent advantages over piloted ones. A sensor can continuously monitor every system without fatigue, without distraction, without the cognitive limitations that human attention inevitably imposes. The timeline for MQ-25 reaching initial operational capability has been a moving target throughout the program's history, as is typical for complex military aircraft development programs. The Navy originally hoped to achieve initial operational capability, the point at which the aircraft is declared ready for deployment, around 2024 to 2025. Development challenges, the inherent difficulty of the technical problems being solved, and the unprecedented nature of what was being attempted have pushed that timeline. But the core program has remained on track in the sense that the fundamental technical demonstrations have been completed successfully. The aerial refueling demonstrations were real. The autonomous flight capabilities are real. The program is progressing toward operational deployment, even if the exact dates have shifted from original projections. The question of what happens when the MQ-25 actually deploys with a carrier strike group, when it goes from test asset to operational weapon system, is one of the most fascinating questions in contemporary naval aviation. The operational patterns will need to be worked out through experience. How many MQ-25s will a typical carrier air wing include? How will they be integrated into daily flight operations? What happens when an MQ-25 experiences a system failure at a critical moment? How will the aircraft's operators, sitting in control stations aboard the carrier, manage multiple simultaneous refueling missions? These are questions that can only be answered through real operational experience, and the answers will shape the future evolution of the program. One of the most important operational considerations is communications architecture. The MQ-25 relies on data links to communicate with its controllers and to receive mission updates. In a highly contested electromagnetic environment, exactly the kind of environment a carrier strike group might face in a conflict with a sophisticated adversary, those data links could potentially be jammed or disrupted. The Navy has invested significant effort in making the MQ-25's communications architecture resilient against electronic warfare, but the details of exactly how this is achieved are appropriately classified. What is publicly known is that the aircraft has the ability to operate with a degree of autonomy that allows it to continue executing its mission even if communications are temporarily disrupted, a critical capability for any system that might operate in a real-world contested environment. The MQ-25's relevance to the Pacific theater, specifically to the strategic competition with China, deserves extended attention because this is ultimately the context in which the aircraft's operational significance will be tested. China's military strategy in the Western Pacific centers on a concept sometimes called anti-access and area denial, or A2AD. The goal of this strategy is to use a combination of long-range missiles, submarines, aircraft, and electronic warfare capabilities to make it extremely costly for U.S. naval forces to operate within a large area of ocean surrounding China's coastline and the various territorial disputes in the South China Sea, East China Sea, and the Taiwan Strait. China has invested heavily in this strategy for decades, deploying increasingly sophisticated and long-range anti-ship ballistic missiles like the DF-21D and DF-26. Missiles specifically designed to strike aircraft carriers at ranges of thousands of kilometers. The American response to this challenge has multiple components, but one of the most important is simply extending the range and reach of carrier-based aviation so that carriers can operate at greater distances from potential threats while still being able to project air power into contested areas. The MQ-25 contributes directly to this response. If a carrier can launch MQ-25s that then refuel fighters at distance from the ship, the fighters can strike targets that were previously beyond their unrefueled reach, and the carrier itself can maintain a position at greater distance from the most dangerous missile threat zones. This is not a complete solution to the A2AD challenge. Nothing is, but it is a meaningful and operationally significant contribution to the Navy's ability to compete in the Pacific environment. The comparison with Chinese unmanned aviation programs is instructive here. China has been pursuing its own carrier-based unmanned aircraft development, and while the specific capabilities of those programs are difficult to assess from open sources, it is clear that China recognizes the same operational value in carrier-based unmanned systems that the United States Navy does. The MQ-25 program represents a significant American lead in this specific capability area, and maintaining that lead matters. The history of military technology competition teaches that advantages erode over time as competitors learn, adapt, and invest. The United States has a window in which its lead in carrier-based unmanned aviation can be exploited operationally before that lead narrows. There is also a broader alliance dimension to the MQ-25 story that deserves mention. The United States operates carrier strike groups in close cooperation with allied navies, and the capabilities of American carrier aviation affect the security of allies across the Indo-Pacific and beyond. Japan, Australia, South Korea, the Philippines, and other partners in the region rely in part on American carrier-based air power as a deterrent against aggression. An American carrier air wing that can project power further, strike more precisely, and operate more sustainably because of the MQ-25's refueling capability is a more credible deterrent for those allies. The MQ-25 is not just an American national security asset. In the broader sense, it is a contribution to the stability of the international order that American military power has underwritten since the end of the Second World War. The engineering team that built the MQ-25 deserves recognition that they rarely receive in the broader public narrative about defense technology. Hundreds of Boeing engineers and thousands of contractors worked for years on problems that had never been solved before. Autonomous carrier landings, unmanned deck operations in a carrier environment, aerial refueling systems optimized for unmanned operation, software architectures that could be trusted with life and death decisions in a naval aviation context. These were not glamorous problems in the way that supersonic flight or stealth coatings are glamorous. They were deep, grinding, technically demanding problems that required sustained intellectual effort and a willingness to fail, learn, and try again. The culture of engineering excellence that produced the MQ-25 is as much a part of the story as the aircraft itself. The test pilots who flew chase aircraft alongside the MQ-25 during its development testing played a unique and fascinating role in the program. These were experienced naval aviators who flew in close proximity to an aircraft with no one at the controls in the traditional sense, watching its behavior, documenting its performance, and providing the human judgment that was essential for interpreting what the test data meant. Their observations shaped the development of the aircraft in ways that pure data analysis never could. When a human pilot with thousands of hours of carrier experience says that the aircraft's approach behavior felt unusual in a particular way, that observation carries information that sensor data alone might not capture. The collaboration between human test aviators and unmanned systems engineers was one of the program's underappreciated success stories. As the MQ-25 program moves through its final development phases and toward operational deployment, the questions that matter most are about how the aircraft will perform in the real world, not in the controlled conditions of a test range, but in the actual chaos and unpredictability of fleet operations. Will the maintenance system work as designed when you are in the middle of the Pacific Ocean with no access to the Boeing factory? Will the autonomous systems perform reliably across the full range of sea states and weather conditions that a deployed carrier encounters? Will the integration with the carrier air wing's operational patterns prove as smooth in practice as it has been designed to be on paper? These are the questions that only operational experience can answer. The legacy of the MQ-25 Stingray, even at this relatively early stage of its operational history, is already assured. It is the aircraft that broke the barrier between carrier aviation and unmanned systems. It is the aircraft that proved autonomous carrier operations were not a theoretical possibility, but a practical reality. It is the aircraft that solved, or at least dramatically reduced, the refueling constraint that had limited the reach of carrier-based aviation for decades. It is the aircraft that laid the technological and institutional foundation for every unmanned carrier aircraft that will follow it. Future naval historians will look back at the MQ-25 the way aviation historians look back at the earliest jet-powered carrier aircraft, as the beginning of an era, as the proof that a new way of operating was possible. Think about what it means that we now live in a world where an aircraft carrier, already one of the most complex and powerful military instruments ever created by human civilization, can launch unmanned aircraft that fly themselves to thirsty fighters, transfer thousands of pounds of fuel with mechanical precision, and then autonomously return to the moving, pitching deck of their carrier and land themselves safely. Each component of that sentence would have seemed almost impossible to achieve reliably just 20 years ago. The combination of all of them, working together in an integrated operational system, represents a genuine technological achievement of the highest order. The engineers who made it possible built something that matters, something that will shape the character of naval power for decades to come. The MQ-25 Stingray is not the end of the story of unmanned carrier aviation. It is the beginning. The technologies it has proven, autonomous carrier landing, unmanned deck operations, aerial refueling at scale, are the building blocks on which the next generation of carrier-based unmanned systems will be constructed. Those future systems will be more capable. They will be stealthier. They will carry sensors and weapons that expand the carrier's ability to see and strike across ever greater distances. They will work alongside human pilots in increasingly sophisticated ways, expanding what the carrier air wing can do beyond what is currently imaginable. But they will build on the foundation that the MQ-25 is laying right now, in the sky above the Pacific Ocean, in the rough landings on heaving carrier decks, in the hundreds of thousands of lines of software code that have been written, tested, refined, and proven through years of painstaking development work. The United States Navy, for all the criticism that American defense procurement sometimes receives, and much of that criticism is deserved, has in the MQ-25 Stingray produced something genuinely impressive. Not just technically impressive, though it certainly is that. Strategically impressive, operationally relevant, timely in the sense that it addresses a real and urgent capability gap at a moment when that gap matters enormously. The Stingray is a name that suits this aircraft well. It moves through the water, through the air, with quiet, efficient, precisely directed purpose. It does not roar or thunder. It glides, it observes, it acts with mechanical calm. And like its biological namesake, it is more dangerous and more capable than its peaceful appearance suggests. The world's navies are watching the MQ-25 program with intense interest. Every navy that operates aircraft carriers, and that list, while not long, includes the most powerful navies on Earth, is studying what the United States Navy is learning about unmanned carrier operations. The lessons of the MQ-25 program will influence naval aviation development programs in the United Kingdom, France, China, India, and every other nation that sees carrier aviation as a key component of its maritime power. In that sense, the MQ-25 is not just an American story. It is a story about how naval warfare is changing globally and permanently. When future generations of naval historians write about the transformation of carrier aviation in the early 21st century, they will identify several key inflection points. The shift from conventional to nuclear propulsion for carriers, the introduction of angled flight decks and mirror landing systems, the transition from propeller aircraft to jets, the development of stealth, and they will identify the MQ-25 MQ-25 Stingray as the moment when unmanned systems became a permanent and irreplaceable part of carrier air power. The moment when the carrier, already the most powerful conventional military instrument in human history, took a step toward a future that its builders in the 1940s could not have imagined. A future where machines fly from its deck not as experiments or demonstrations, but as operational members of the strike group, doing their part, contributing to the mission, extending the reach and power of the force. That future is here. It landed on the deck of an American aircraft carrier with the quiet precision of a machine that has calculated every variable and found its answer. And in that landing, in that controlled, autonomous, historically unprecedented moment, the nature of naval warfare changed. Not with a bang, not with a declaration, but with the silent, efficient, perfectly executed landing of an aircraft that nobody was flying. The MQ-25 Stingray has arrived, and the age of unmanned carrier aviation has begun. If you have followed this story from that first unmanned flight over the skies of Illinois to the strategic implications rippling across the Pacific, you understand something that most people, even many who follow defense news closely, have not fully grasped. The Stingray is not just a tanker. It is a declaration of intent, a proof of concept, a foundation stone. The United States Navy has demonstrated that it can operate unmanned aircraft from its carriers, and having demonstrated it, it will not stop there. The story of the MQ-25 is still being written, mission by mission, landing by landing, gallon by gallon of transferred fuel. And every chapter of that story is pushing naval aviation further into a future that is more capable, more complex, and more consequential than anything that has come before. So here is the question I want to leave with you today, and I genuinely want you to think about this carefully before you answer in the comments below. Given everything you now know about the MQ-25 Stingray, about the range problem it solves, about the autonomous technologies it has proven, and about the foundation it lays for future unmanned carrier systems, do you believe the next carrier-based unmanned aircraft the United States Navy develops should prioritize strike capability and stealth? Or should it continue the MQ-25's legacy of prioritizing operational integration and reliability? Should the Navy go bold and build the unmanned strike aircraft that UCLOS originally envisioned? Or should it continue the patient, step-by-step approach that made the MQ-25 a success? Drop your answer in the comments. I read every single one. And if this video gave you something to think about that you did not know before you clicked play, hit that subscribe button right now. Because this is exactly the kind of deep, detailed military history and technology analysis we do here every single week. Do not miss what comes next.